Okay, welcome to this next installment of the webinar series presented by the RSNA 3D Printing Special Interest Group. My name is Ken Wang. I serve as the liaison from the 3D Printing Special Interest Group to the Radiology Informatics Committee. Today, we're fortunate to have Adam Wentworth from the Mayo Clinic speaking to us about automation in patient-specific design. And, I've been looking forward to this session personally, not only because creating anatomic models and guides is time intensive, and so methods to increase our efficiency are certainly welcome, but also because automation can increase quality by improving consistency and reproducibility. Now, before we get started with Adam's talk, I do want to mention that the 3D Printing Special Interest Group is part of RSNA and represents a community of experts doing 3D printing in a wide range of clinical areas. Beyond clinical applications, the SIG also works on issues related to training and education, research, workflow optimization, which is what we're talking about today, regulatory considerations, coding and billing, and many other aspects of the clinical practice of 3D printing. And if you're not a member of the SIG, please check out this QR code on the screen to learn more and find out how to join. These, by the way, are the current SIG officers: Lumari Santiago at MD Anderson Cancer Center, Beth Ripley in the Department of Veterans Affairs, Summer Decker at the University of Southern California, and David Ballard at Washington University in St. Louis. I also want to mention that the SIG is hosting a CME course next month. That's actually 1 month from today in Chicago. That course is called RSNA Medical 3D Printing in Practice. And here's another QR code for more information, including the meeting program and the registration link. So please check that out as well. All right, so now on to our speaker. Adam Wentworth is a senior clinical engineer at the Mayo Clinic Anatomic Modeling Unit. And Adam graduated with a master's degree in material science and engineering from the University of Connecticut. After obtaining that degree, he stayed on in a staff role, and he was an advisor to the 3D Printing Club, and he co-taught an undergraduate course in additive manufacturing. He then moved to a staff role at MIT, where Adam developed early-stage medical devices for sustained drug delivery. His prototypes have landed in the hands of Bill Gates and have been exhibited in the Smithsonian Design Museum. At Mayo Clinic, Adam designs patient-specific anatomic models and surgical guides for a variety of surgical specialties. He's a proponent of extending the reach of patient-specific medical devices and enabling mass customization through workflow development and automation. And again, that is his topic for us today. So without further ado, I'll turn it over to Adam. And Adam, thank you for being here.
So much, Ken, for the introduction. It's a pleasure to present to you today and to share the work that we've been doing for the past couple of years in automation. I'm hoping to showcase some of the demos of some of that automation past what I presented at the SIG a few months back, and looking forward to some questions at the end of the presentation. So I'd like to start with saying that automation is not just what I talk about today, but it's a wide range of technologies that's aimed at reducing human intervention. That's through predetermining decision criteria, such as engineers who know how to 3D print, kind of baking that knowledge into the process, and embodying those predeterminations in machines, like we're going to do with some programming today. As a disclosure, I'd just like to share that I am a shareholder of Materialize. And for the scope, I'd like to say that scripting has personally increased our efficiency, standardization, and the quality of our printed models and guides. I'm going to showcase some examples and demonstrate how everyone listening could get started with scripting to automate some of their own workflows. And that automation exists out of design, including in our manufacturing execution systems, AI-assisted segmentation, post-processing, and some pipelines to AR, VR applications, which seem to be ever increasing. This is our location in Rochester, Minnesota. This is our St. Mary's campus. So we're in there, and there's a downtown campus as well. Mayo has a long history of mixing engineering and the clinical practice. And so it's kind of the natural birthplace of printing at the point of care. Our director, Jonathan Morris, and past co-director Jane Matsumoto Started the lab 17 years ago. The first case was a pair of conjoined twins that they helped through medical illustration and a 3D printed model of a liver to successfully separate those twins. And, it was a slow trickle of clinical cases after that, but with their vision, it gradually increased. And so with that increase was adjusting to growth with a small team. Everybody was kind of wearing a few hats at that time, developing new applications for standard of care. Right now we're doing, probably 50% of our cases are mandibulectomies and maxillectomies that are guided with fibula guides, fibula-free flap operations. They developed quality standards using this, phantom that's being printed. And also standardizing data handling is a big part of allowing these labs to grow large, because it gets unwieldy pretty soon to kind of manage everything in Excel sheets. And here we are today. Our team of 15 has an annual output of about 900 anatomic models and 1,200 surgical guides per year. And that's in addition to other ventures in AR, VR, research through residence, simulation, and education. And so here's the clinical workflow. You can see that I've enlarged design. Design is that critical piece where we're limited by technologies of imaging and 3D printing, but also needing to meet the user needs of the surgeons for a variety of different applications, especially tying those needs to folks who don't necessarily know what 3D printing can offer. So we're torn between a few different places, and design is sort of that critical aspect of, there's a little bit of subjectivity in how an engineer might design a specific part for a specific application, and hopefully automation can sort of nail down the critical factors of any one of those designs, or a workflow that gets really well established to help define it well. And so I'll say to err is human. Over the past few years with a growing team, growing applications, you can easily see where certain parts of the process are more prone to potential human error. And those include design risks for models that require either a high technical aptitude of software, models that are high complexity, like this liver model that we did fairly recently, or models that require high speed. Not everyone is perfect in when they order 3D anatomic models, so you can definitely come up against it sometimes where things are due in a few days and you really need to do the segmentation, because having a model is better than not having a model. And so to do those same things quickly is also important for the clinical practice. So I'll say after developing scripts over the past couple of years, they largely fall into two bins. I use a cloud for these general use type of scripts, which tend to be smaller in size, more broadly applicable, used in conjunction with other application-specific scripts, which I represent with this puzzle piece, because they fit a very specific place in our workflow. They have very well-defined input parameters and may be tied to a specific surgeon. Surgeons here, they tend to love the way that they're doing something, and they want to keep that very consistent. And so the scripts are a great way to keep that consistency, and it doesn't matter which engineer is working on it. And so that's not the same thing you may experience when going to a med device manufacturing company, that you may work with different engineers each time and they don't know the specific wants and needs that you have. So we'll showcase some of those here. This general use script is an automatic coloring script. And so we found out, we can have this table of RGB values, and maybe we give that in an SOP to a new engineer. But just because you give someone documentation doesn't mean it's super easy for them to do it every single time. And coloring is a very simple type of task in the software, but being able to do it exactly the same every time is really the job for a program to do, not a person. So being able to turn this pelvis into standardized bone colors, standardizing what a cyst or a tumor color is really important from the surgeon's point of view, so that it's very intuitive. When they hold a model in their hands, they don't have little annotations that tell them what part is what anatomy. So standardizing that with colors and doing that across the board will help new surgeons also kind of pick that up really quickly, because they've seen models before and they know what color to expect of a certain type of anatomical structure. It also lends itself to some kind of personalization. Through automation, these demo hand splints get broken up into thousands of surfaces and randomly colored using a color palette that's defined. So, having things for pediatric patients or things where, aesthetic may be a larger part of the performance value of that object, enabling customization through that easy scripted thing is a big advantage. Here's another type of script that we use where we're hollowing out very large, dense objects. Could be organs, could be, in this case, blood vessels, where a user can select a point on that object, and based on a printing technology that's also selected, we'll choose a certain size thickness of the walls and a certain size plug that plugs up that hole. And you might say, like, okay, we can just, cut a cylinder out of a hollowed object. But the cool part of this is that it retains the normal conformity of the outside structure by making that plug also conform to the original shape. So this is just a pulmonary example. Here's another application-specific script where we started with, development on this, and design was all manual, and could be tedious based off of the surgeon preference. So pectus excavatum is this sunken sternum, and to fix that, you put NUS bars across the ribs and underneath the sternum, like this. So in our segmentation software, we're able to draw contours to represent sort of the normal convexity of the rib cage. We can take those curves and put them into our design software, and the script will generate these molds, which are used to bend plates intraoperatively. We do that versus pre-bent plates because surgeons may change their mind in the operating room, and so it's nice to have this as a starting point for them. And this has become standard of practice. These are ordered for every pectus excavatum from the surgeon. This is the final print with a replica NUS bar included. So the script generates 2 mold halves designed to be printed on the Form 3B. It's a little bit smaller of a build volume, so splitting models in half that can kind of be puzzle pieced together ensures faster print time. And the mock NUS bar will give them some reference to what it should look like at the end. Our kidneys are probably one of the best examples of an application-specific script that saved a lot of engineering time. This also utilizes an auto coloring script as part of it. So it starts out like this with kind of crazy colors that you get from segmentation. This just happens to be a horseshoe kidney that's connected at the posterior point, at the inferior point, sorry, and with a little bit of segmentation artifact. So with this, you have very fine vessels that are represented as well. So the script goes through and automatically colors these parts. It makes a lattice out of the kidney. It adds cones to support during multi-jet fusion type printing. It adds fiducial markings and a base and a label to identify. So I wanted to jump out and sort of do a little more show than talking. And so I'm gonna run this script. I'm not sure exactly how to put this up, but we'll start it running. You can see it live. So in the background now, it's wrapping all of the vessels. It's keeping a copy of all the original parts. It's coloring all of the parts based off of the label of the part in the object tree on the right side. And this is on a very low power computer, just so just so everyone's aware. It's not this is nothing high powered running this currently. Typically, while scripts are running, also it's a great time to get a cup of coffee, go to the bathroom. It's a big advantage for less human interaction time, and it's still like doing all of the design work in the background. So I expect this to run for about a minute, and then we can do the rest of the kind of user interaction heavy components at the end. Another second or so. All right, so there's a message box that's popped up. Most of the design work is done at this point. It's asking the user to orient in a specific view and indicate a point on the model to place the CAD file, which is the base. So I'll click a point here, which will import the base. It's asking the user to input to move the build plane. So this is a virtual build plane of where the part would be printed on a printer. Make it not intersect the part, and then type escape when you're finished. So here it imported a build plate where it thinks it might want to live. The reason we're doing the support structures in this case, especially with a tumor on a lattice, is that you have a heavy object which could deform this delicate lattice structure while the powder is still warm. So we would actually prefer to translate this build plane above the object to support the tumor from the other side. So we're going to do that. And then we're going to hit escape. It's asking me to indicate 3 touch points where these cones will touch the model. So I'm going to hit OK. And I'm going to hide this build plane so I don't click on it by accident. We generally make these cones in a large triangle structure to be supporting evenly from all sides. That's why I'm making this big triangle with 3 points. And then it's asking me to trim these structures, which I can do after, so I'll skip that. And indicate 3 points. This is another general use script that's been incorporated. So this is including fiducial markings. So 3 points that'll be measured from their nearest surfaces. You'll see that. Here's a point where we would usually take a screenshot as part of quality control. When the object is actually printed, our technicians will measure the distances between these dots and confirm that they represent within tolerance accuracy to what's been done digitally. Here's where we can input a unique identifier. And we can indicate 2 points where that label should be placed. One is a starting position and one is a direction indicator. There's a note that says the script is complete, and that's the finished product. We could then do some simple quality control where we didn't trim things before, but we can do that really quickly. We might also double check the center of gravity of that base. Make sure that the model's not going to tip over when it's printed, so I might change that slightly. But overall, that's about 40 to 45 minutes of design time done in about 5 minutes. And that's kind of the general theme that we see across the board for the scripting is that it's about 80% time decrease. So here's the finished model that's been printed with the ID blurred out. So I showed the plug script, which will save you about 65% of the mass of the entire part. But if you use a lattice, that's about 97% reduction in material. So that's a nice savings. And anyone who knows the business side of 3D printing, material equals money. Usually the cost per part is dominated by material costs. We have a performance type script which runs alongside all of these and collects data in the background. So it logs how much time the script is running for, who ran it, and what script it was. And that enabled us to generate this data. After 6 months, I went back and plotted, had to do some manually to record the manual times, but then the scripted operating time of a script and the number of clicks were also counted, resulted in about an 80% decrease in the amount of time that it took from the engineering side. So that's a significant change, enabling us to really process a lot more models when the bottleneck of an operation is engineering. That's a big point. Now this leads into the appropriateness and value equation for 3D printed anatomic models. Incredible work has been done by the SIG and Ken leading this registry for data collection by longitudinal studies, which demonstrate more of a granular basis for the value of each of these models for specific applications, such as percent revision or blood loss, things like that. At the end of the day, my role in this is hopefully to show that we can decrease the cost per part, because that shifts the whole equation to making higher value for all anatomic models across all specialties. So I think that's a big part of the equation that sort of the data needs to be filled in there. And lastly, I wanted to highlight some of the scripting for research, which I've done more recently. And I think one aspect of scripting is enabling non-expert users to process large amounts of the 3D data. We have the benefit of residents coming to our lab and really wanting to utilize 3D data to prove out their hypotheses for certain aspects. Knowing that 3D is better than 2D for planning in a lot of circumstances. These are just a couple highlights of ongoing research where we've thought about the problem statement that the residents have given us and how we might automate that with a script. So this tibial plateau fracture, we're analyzing the volume of the gap spacing between all of those fragments and seeing if it has a correlation to outcome or to search a full outcome. And we're being able to process 300 tibial plateaus for this. Statistical shape modeling is has a large potential for this, where we will take large amounts of a single type of bone. For example, the bones you see here is a humerus and skulls. And there's a lot of prep work that goes into preparing models to generate a statistical shape model, which is essentially an average out of all of those that is warpable in non-uniform manners. This is what some large med device companies will use to develop custom implants, and it's all about the mesh in that case. A third one is bone morphometry and anatomic axes for implant planning. So it's really advantageous if you're able to evaluate bone shapes to pre-select implant sizes and evaluate and kind of pull out the anatomic axes from a bone so that you can appropriately place implants in their correct directions. And lastly, we've done some recent range of motion mapping. So I'll show that soon. Here's an example of some of this code. This is used in some range of motion where we're writing to Excel sheets with some data, and we're iteratively rotating models until there's a collision that is detected. So we're using this collision detection function here. This is our surgeon, Dr. Havesi, showing me in one of our first meetings where this area of ischiofemoral impingement happens and how he wants us to sort of try to analyze that. Here's an output of the script where we've allowed the femur to rotate about the femoral head, approximating it with a sphere, and rotating it in different directions until it collides with the bone. My colleague Megan has developed a subsequent script which highlights those areas of bone which have collided and highlights them red. So if they're doing some arthroscopy where they're going to mill out some regions of bone, they could tell where they need to mill on those on a patient-specific anatomy. So I'd like to demonstrate to showcase at least the output data from that range of motion script, and to show you how our resident will post-process this data. This is to showcase that automation doesn't just live in the 3D design software, but Excel has a few nifty things too as well, through macros. So the data has been output here in terms of different clearances between the collisions for data points in external rotation, adduction, and extension. And through a macro that's been recorded, we can automatically make plots of all of these data points, how the surgeon wanted it. And then we can reformat those into something that's a little more workable. I'll just back up here to show you there's 9 plots here. And now this is something that a resident could do all by themselves without much experience with the software. It's simply running Python scripts and providing input in those user interactions where it's needed, and output some plots in half an hour would be a reasonable amount of time to generate this data. And they can rinse and repeat for now many different patients' anatomies. And you can see how quickly this becomes useful. So you might ask, how do I get started? The first basic things you need, we are using materialized software for this, and which uses Python. So you would need a Python interpreter. Most versions will be using the 3.8, and the newest version uses 3.10. You need some IDE or a program that will allow you to write code. The code that you've seen so far is called Visual Studio. So that's a link I've provided here. You need the application that's doing your 3D modeling, and you need some functions that are provided by that software. And disclaimer, I'm not a computer scientist, I'm a material scientist. And so most of this stuff I've learned over the past 2 years. And I took a Code Academy course a long time ago to learn some really basic Python. And a lot of the rest of it I've just learned as I've gone. So I'd like to show you how you might get started with writing your first script. It's going to include terms like pseudocode, which is, kind of roughing it out in terms of, what functions do you want in it? What's the order of operations? How are you going to fill those in? Some other really basic functions are like finding parts, other core functions that you might do for a general use script, things you might do for every case. And then for loops to really process large amounts of parts where you're going to do the same function to all of them. So let's jump over to that. So this is Visual Studio Code. And on the left, you're going to see this sort of template pseudocode that I've written for an example of a first script. Something that's good to note is you might generate IP when you start doing this kind of stuff because you'll find it has value. So you might be inclined to put your name on it, put the date that you created it. Important for running software, especially for healthcare, for medical devices, anything like that, is putting the software version that you've been using in there. And whenever you do validation, that it's tied to a specific version because software versions change all the time. And it's important to run the scripts in the correct version to ensure proper output. Here I have intended use of the script, which is a really basic description for someone who's never seen it before. It's the first time opening, to tell them what the script is supposed to do to give them the expected inputs and outputs of that script. The first thing that we do is import a package. In Python, that means a list of functions that become available to us. So for thematic, it's import trimatic. The next thing we can do is set a view orientation. We do that with this trimatic view custom function, which is giving us two vectors. One is pointing into the screen and one is pointing in the up direction. Next is getting a list of all the parts. This function called getParts returns the entire list of every single part in your object tree. Some things are not parts, like analyticals or measurements or angles. Those aren't parts, so they won't get returned here. A great thing to do when you're just starting is to duplicate all of your original parts. As you're developing, you're going to make a lot of mistakes, and it's much easier to have a copy of those original parts to restart the whole process rather than close and reopen the whole file. So we found that to be pretty valuable. So it's going to run a for loop for each part in this list. It's going to duplicate that part. Then we're going to make a list of just those duplicated parts through this find parts function. And you'll notice there's an interesting character here. With find parts, this becomes a regular expression term, which is kind of like a wild card. Anything could be in there, and we'll return a list of anything that has underscore duplicate at the end. And that gets generated whenever we duplicate a part. This is now renaming the parts. So by running this function, we're eliminating the underscore duplicate and replacing it with nothing, which gives us the original name of those parts. We're also hiding them. Then we're creating a group called originals of all the duplicate parts. And here's our for loop that's running on the parts that have not been grouped. And we're doing basic functions that you might do to every part, which is a reduce, a smooth, a fix. And then we're putting a tag called -fixed on the end of the name. And then for fun, we've included a message box, which is telling the user to select a specific part. And what they're going to do with that is we're going to get the selection and we're going to color that part red. An interesting note here is that RGB values are represented as values from 0 to 1. So instead of 255.00, it normalizes to 100. And at the end, a nice thing to do is print indication that the script is finished. That's just a notification to the user. So now we're going to run this exact script on one of our pelvis models. This is a model exactly how it's come after radiologist review. And we would likely do some reduced and smoothing functions on it. This looks pretty good. So let's do that. So we've only got 4 parts in our list here. Pretty easy. All right, we're going to select one part to become red, so maybe the hardware. There, I turned it red. Now I'm going to run our auto coloring script on this as well, just so you can see it. And you've seen how quickly that works, where it's coloring all the bones, a bone color, and our standard color for hardware is blue. So you can just see how much time that saves. Now, if I wanted to get back to my original files really quick, I could delete these that have been changed, and I can just ungroup that folder, show these parts, and I'm back to what I started with. Ooh, it looks like the coloring has also colored the parts of the group too. So here's to showcase some of the automation that exists outside of our design phase. One is AI segmentation. Right now, we've got scripts for spine and CMF and lower extremity. It's really saving a ton of time and increasing the quality of each of those exported models. Once you're able to segment at a high rate of speed, you're also able to unlock new applications that might be time sensitive, such as trauma cases. Very interesting. Here's an example of some things we do with design not done by the engineers, they're done by practitioners. So some software tools are enabling also novice users to get involved in the design phase of these med devices. Currently, we're doing splints. Our dental specialties are using intraoral scanners. These videos are not my own, so just be aware that they're from third parties. But the general theme is that we're simplifying user inputs. These things that are designed outside of our lab are generally enabled by 3D scanning technologies of various sorts. So you may see blue light scanning or for intraoral scanning. You may see structured light scanning for orthotics, which is very common. Once you take the design out of the 3D lab, you're kind of freeing it up for larger volumes for multiple practitioners to be involved, to really make it exactly how they want it. Build preparation is also becoming more advanced over time, and this is through no cause of our lab. These companies are enabling packing algorithms to pack higher densities of parts into printers, higher utilization of powder. Like I said, the material cost is one of the largest costs of parts, and packing parts automatically will drive cost savings, as well as eliminating user error of any overlapping parts. If you try to do this manually, you definitely overlap a few parts, and both of those would then fail. Manufacturing execution systems. This is largely tying together all of the data streams, enabling you to do better analysis of data at the end of the year when you're really asking, well, what technologies did I use? How big were the parts that I printed? It can really drive strategic decisions on what types of printers should we get in the future, what is most in demand. Networking with printers is also enabling a lot less manual data entry through the real-time status of printing parts, through data collection on material use, printing time, and just kind of like filling in any data gaps. If you have manual data entry, you're going to end up with data gaps. And we're really hopeful that this type of system will also automate the dictation, which a lot of radiologists would appreciate, that all the data that's involved in a case could automatically be put into their template and used for billing at the end of the day. So I want to acknowledge all the folks that have helped out with the scripting. I just really appreciate that my work is helping to inspire a lot more people to start scripting. And as a former teacher, former academic, nothing gives me more satisfaction than to see other people succeed. So I do want to give acknowledgements to all these folks. So thank you for listening, and I would love to talk to all of you about automation.
Great, Adam. Thank you so much. That was really chock full of ideas and examples, and I think you really showed us so many ways that automation and scripting in particular can help with workflow. You talked about time savings and material savings and reducing the cost per part and increasing kind of the throughput capabilities of a research effort. So many different ideas. Really appreciate that. I see some questions in the chat. I also have a number of questions of my own, but let me defer to the chat first. I'm going to read this one, and I think there's maybe a couple of questions embedded in here. This one says, do you have a standardized imaging sequence that is taken as input for these scripts that involve segmentation? In my reading of that question, I think, well, part of this is about imaging protocols, which you didn't say too much about. But also this question is asking perhaps about segmentation. You did mention AI-based segmentation. I wonder if you just comment on that.
Yeah, absolutely. Yes, and I will say that because we do such a large volume of printing here, we do get outside imaging as well from time to time. And that has to be really carefully evaluated for does it have the right amount of quality for us to work with in the first place? I think there are some folks out there who've helped define those standards on acceptable imaging quality. And what I will say is we do have many internal imaging protocols that are developed, that are created specifically for segmentation for a 3D printed model to be made at the end of that. And I'll comment a little bit more about the kidney specifically. The kidney takes a multi-series imaging requiring contrast and imaging at different points in time to capture arterial, venous, nephrographic, excretory phases. And co-registration of each of those image series is makes our job a lot easier. I won't say like it's absolutely 100% necessary, but I will say it makes the job 100% easier on our endpoint to make sure that the models are also accurate. That includes same positioning of the patient between scans, slicing thin slices. So yes, we do have specialized protocols for kidney and many other things that when orders come in and tying to the patient record to make sure that quality is there from beginning to the end. For AI segmentation specifically, I will say we do work with a third party and that training data has been generated by us. So our gold standard segmentation data has gone in to train those models. So we have a hand in making sure that the quality was high enough for training as well.
Yeah, that's great. Maybe to follow up on imaging protocols, I was wondering if you have any strategies or methods that you use to automate the ingestion of imaging for segmentation. And so here I'm talking about filtering or cropping or other image pre-processing steps that you might do in a kind of a prototyped way for certain applications.
Personally, I've found that doing those pre-processing steps, at least in our software, is very cumbersome. It's very slow and not always needed. We haven't found a need to really do that for a large amount of our applications. It could save file size, but I don't think that's necessarily a driver for us to do that. We essentially are relying on good reconstructions of those raw images to have IMAR, to have soft tissue kernels, things that just make the segmentation work, rather than worrying about it after the fact.
Makes sense. We have more questions in the Q&A, so let me go to one from Todd Piatilla. So Todd says, great presentation and demos, I agree. Have you experimented with generative AI tools to assist with generating code for your scripts?
Maybe in like really initial development phases where, because I'm not a computer scientist, I rely on some of our local experts for specific functions that we have yet found solutions for. I don't know that, none of that code gets copied and pasted directly into our code, but we essentially use it as figuring out, oh, that's how you might do this type of operation. I think one of our current challenges is tagging parts with metadata. So we're going to look into, ways that we might do that. Yeah, really basic stuff like writing data to an Excel sheet, things like that, where for our initial kind of scoping out or proof of concept work, we could look to ChatGPT or some other generative AI like knowledge bases for some really basic information.
Yeah, makes sense. And here's maybe a follow-up I'll inject on this one also, which is, have you found that there are things you would like to script that are not currently scriptable in the APIs that you have?
All the time. I will say we keep a running document, or I keep a running document of ideas that I have not implemented yet, just because I don't have that much time to be doing it. But there's always, once you start down this path, there's an endless road of, hey, maybe we could automate that, right? And so it's a good idea to keep those thoughts together someplace, because you may work on current projects that result in solutions for those ideas that you have queued up. So we've seen that for some other times. And I will say that also working on these general use scripts is also helpful, because these are essentially little standalone modules that can be puzzle pieced together with some of your other ideas and make a really nice, complete, finished product. And you had half of the work done already.
Yeah, makes sense. Here's another question. This one comes from Brian Patterson. He says, great talk, thanks for sharing. And he asks, what is your QA process like to verify that your scripts are not modifying the accuracy of your finished models?
I think end of the day, you are copying and pasting back into your segmentation platform to ensure accuracy. But I'll also say that the script itself is largely a manifestation of what you would have done manually anyway. So and that ties to repeatability of your process. You're not going to script everything, but you're going to script the things that you are clicking the same buttons for this type of model that you do regularly. I will say that there's a bit of intelligence also baked into that. So you can build QA into the script as well to perform some of these checks along the way. For example, the fiducials that I marked on that model, we will check, we'll do calculations within the script to check it's within a certain range of acceptable values, or we do that during development. We have this the script for preparing models for the statistical shape modeling. We will check if certain parts are outside a certain bounds of a surface area to volume ratio. And that would indicate to us that there may be segmentation errors with that model. Say a model didn't had internal cavities that weren't filled, that yields additional surface area, that throws that calculation outside a standard deviation value, and that gets brought to the user's attention by pausing at that point and asking the user, what do they want to do about that part? So there's clever things that you can do within scripts to also check QA.
Yeah, interesting. So automated like sanity checks and other quality checks that you can bake in. As a follow-on to that one that I'm interested in, you mentioned this idea of practitioner design, which I thought was very interesting. And I wonder how you think about QA in that context, if it's really kind of clinical end users who are kind of driving the design process. How do you think about QA there?
I think at the end of the day, it still runs through an engineer to look at. And so some of those applications, they handle the QA in the cloud. They do their own kind of analysis on the meshes to start with. But practitioners are not engineers for sure. And the mistakes could be made as far as choices around 3D printing technology or what have you. And they're obviously very busy people as well. So I would say inevitably it has to go through the eyes of the engineer who's responsible for the printed part to do final QA on those anyway.
Mm-hmm. Makes sense. All right, here's another question. This one looks like a two-part question. First, it says, does everybody on the Mayo team use these scripts, or is it only you, Adam, and a few others who use it? And then a second question, what is your process for speeding up the printing, since you mentioned trauma cases and the print time is clearly another kind of delay factor?
So yeah, I believe it's becoming ever more prevalent. I think everybody is using scripting in some way. I don't know that everybody is physically writing scripts, but everyone is, I will say the route of development of the script is, first it's the idea, it's the pseudocode, it's a proof of concept script that runs on one file or even a simplified file. Then it's tested on past patient data and tested on a lot of different types of anatomies to tease out variability. And then it's put in the hands of a novice user. The user may not be familiar with any type of scripting, but it's put through their eyes to say, hey, can you run this by yourself? Where do you run into issues? Give us feedback on what you like, what you don't like, what you would change. And I think all of those development steps are very, very helpful to produce something that is useful and robust. And so that's essentially, people are using them in different ways. And I'll say our new engineer, I've successfully inspired her to start scripting as well. And we're doing recurring meetings around scripting and scripting challenges akin to an IT group doing Agile or Scrum or these types of workflows where, you know, we ask each other how to solve these problems. And so I'm all for it.
Great. And then again, there was that second question about trauma cases, and can you speak to the time for printing in the context of trauma?
Yeah, so specifically with trauma, typically when we're asked for models, the deadline is not immediate. The deadline is a couple of days because the patient may have swelling that needs to decrease before they go in to do reconstruction. And so we typically do have a couple of days, but the design piece doesn't become a barrier to it anymore. And I think also the surgeons are a little more comfortable with asking for something that's due in a few days when they know that we have the capability. Sometimes I think surgeons are a little bit hesitant to say, maybe it's too close to the deadline, so they might not even bother. But giving a surgeon confidence to say, I know that team can do it, helps us get those kinds of orders.
Mm-hmm. Yeah, that makes sense. Here's another question asking about color coding. When you color code the anatomy, is that color assignment being translated directly to the 3D printing software?
Yeah, so all these parts that you see on the screen that are multicolor are exported as OBJ files. That's a single file, and all the parts are embedded within that, and those assigned colors go with it. So yes, it does go to any multicolor 3D printing as an OBJ file. We'll have those colors baked in.
Mm-hmm. Great. Here's another question that I have, which is you've touched on the AI segmentation a couple of times now. You said that the training of those tools was based at least in part on some of your own local data, which is great. You also mentioned use of those tools for spine, CMF, lower extremity. And is that, when you say lower extremity, I presume that's mostly bony targets also. And so I'm curious if you've had much luck in using AI-based segmentation for non-bony structures.
Yeah, so the lower extremity also includes arterial phase.
Mm-hmm.
And largely this tied with CMF for fibula free flap operations, so that we need fibula bones included in that. So that speaks to, you know, what applications do you do first? It's the ones that you do the highest volume of, or that are most tedious to do manually. So spine is super tedious to do manually, and CMF for us is a large volume. I would say that the CMF and lower extremity are things that are still in development, but are still useful to us.
Yeah, and with regard to spine, you showed that one great image with level by level segmentation. And I'm curious to know a little bit more about that. I think it's often the case that the patients who are most in need of 3D printing are those that have the kind of the most progressed or end stage disease. And do you find that the spine segmentation continues to be useful in spines that, you know, may be not as quite nice looking as that one?
Yeah, in fact, we've run on some extraordinary case, and I will say that some of that AI segmentation, it really depends on what kind of data you're training it on, and you may split that into two separate type of trainings, or not two separate trainings, but two separate kind of weightings. If you run a script of segmentation and it does not perform well on that spine that maybe it's an extreme case, we do use an alternate script that is more designed for stuff that's outside that box and that can handle that more abnormal anatomy. But it does not, for that one, it does not separate each vertebral body separately. Instead, it will segment bone and things that are not bone as a simplification.
Mm-hmm. Great. Thank you for that. And we've answered most of the questions or all of the questions that were in the Q&A. And again, I think you've given us so many great ideas to think about and ways to kind of maybe consider bringing some of this into our own workflows. Here's another question that's popping up. Is there intent for scripts and automated segmentation services to be open sourced or to remain proprietary in future iterations?
It's a
And I
good
know that,
question.
go,
You
go ahead.
know, I think we are not the ones who would be, you know, selling scripts, for example. I think that because I've demonstrated that there is such a large value to those, that the folks who are in the business of medical modeling be the ones to sort of drive that. I know that there are a lot of cloud-based segmentation services, so there is payment for doing those, and that's not a script that's like owned by the user. It's a script that's being rented essentially for segmentation use. I do see value in AI segmentation that's driven by very large amounts of training data to make sure that, you know, accuracy is high, validation is very high. And I think there's a group out of, I want to say the Netherlands or Germany, that I think does have an open source segmentation script that may be on a large number of anatomical structures.
Yeah. Okay. Yeah. So there are different tools out there that people can certainly investigate. All right. Well, we're coming down to the end of the hour. Adam, I just want to thank you again for such an excellent talk and giving us so many great ideas. I also want to mention again the upcoming RSNA Medical 3D Printing in Practice course coming up 1 month from today in Chicago. Please do check out this link for more information. And with that, we'll bring this session to a close, and please stay tuned for the next installment of the 3D Printing SIG webinar series. Thanks again.